there we're recording. Yeah, so welcome everyone to this week's colloquium, and it's my pleasure to introduce to you Fabian Schneider. Fabian is currently a staff astronomer at the Heidelberg Institute for Theoretical Studies in Heidelberg, Germany. He got an ERC grant. I think it's now, is it 1 year ago, Fabian? Or
I just started in January. Yep. So I got it roughly half a year ago or so.
Yeah. So Fabian is building a group now, and as you can see in the background of this first slide, he has some really exciting topics going on here with interacting binary stars, and I think primarily from the theoretical point of view. So Fabian graduated from his PhD in Bonn in 2015. And then he moved on to Oxford in UK as a Hinze Fellow. After that, he won the Gliese Fellowship and moved to Heidelberg University. And after that, now then, he's starting this ERC grant. So I think that this will all be really exciting. And I encourage you to ask questions to Fabian afterwards, and talk to him if there is still slots in the schedule. You should have a look at that. Anyway, so with that, I want you to give you the floor, Fabian. Go ahead.
Ilva, thank you so much, and it is really wonderful to be here with you guys, and it's fantastic that you invited me over for this virtual seminar, because nowadays it's always so complicated to really meet people and get in touch, and this way is really nice, and I appreciate it a lot. So as Ilva said, I'm going to talk about neutron star and black hole formation in binary stars. And this is primarily going to be a theoretically oriented talk, but I try to make it as, I think, approachable as possible. But I guess I'm going to fail in a couple of instances, but hopefully you can tell me off at that point then. So I would like to really start with a bit of a broader introduction, and I would like to share with you sort of my excitement for massive stars and stars in general. And as you all know, stars are essentially the basic building blocks of our visible universe, and they have essentially transformed the cosmos from the beginning on up to this point where we are at the moment. So I really just want to show you the whole evolution of the universe from Big Bang up till today, and I just would like to highlight a couple of points here. First of all these stars have built up the chemical elements that we have heavier than helium in our cosmos, which I think is an absolutely fascinating topic on its own. And I particularly enjoy working with massive stars. And as you know, these massive stars, or these beasts, are literally cosmic powerhouses. And for example, if you already look into the epoch of reionization, you can see that the very first stars, they have greatly helped to reionize the universe. And also, if you look maybe into some other galaxies in here, and you study what the stellar feedback is going to do to such galaxies, you can observe that these stars have extremely strong stellar winds, but they also go off in supernova explosions and so on. And this is also particularly the case in this galaxy here, where you can see the ejecta or the feedback that is thought to be driven by massive stars out of the plane of the galaxy. And I think this is just a fascinating topic on its own. And as I already mentioned, stars undergo spectacular transients, maybe terminal supernova explosions. This is probably one aspect, but also have in mind gravitational waves, of course. I do have in mind gamma ray bursts. And in particular, these transients allow you nowadays to essentially probe the whole cosmic evolution, sort of essentially from the very first stars that were born up until today. And I think in particular in your institution, you have a really long history in building up transient searches and finding, for example, the accelerated expansion of the universe with type 1a supernovae. And at the end of the life of massive stars, you have these black holes or neutron stars. And this is what I would like to talk to you today about. And these objects itself are extreme physics places, and they're fascinating objects to work with. And I already mentioned nowadays that you can measure the mergers of these objects via the gravitational wave radiation. So this is the whole landscape of massive stars and stars in general that excites me a lot. And a couple of years back, we have witnessed, let's say, a paradigm shift in massive star research. And this paradigm shift came into the place when we realized that essentially most massive stars don't live alone, but they have a binary companion. And this is an artistic animation that shows you what happens in such a binary system. So you have a more massive star, the whitish object here, and the bluer one is the initially less massive star. And the more massive star has evolved off and became larger in size, and then it started a phase of mass transfer onto the companion. And this mass transfer phase has now several implications. One that you can already witness here in this animation is that you strip off the envelope of the star. And then the star, once it is going to explode in a supernova, I think it's about now, that explosion is going to be then of type 1b or 1c because the star doesn't have any hydrogen left. And this, I think, an interesting consequence. And as I'm going to show you in a moment, this has actually also a lot of consequences for the stars itself and also for the final fate and so on. But more on that a bit later on. You might be worrying now, why do we really have to take care of all of these binary stars, and what is the sort of the thing that has changed since, let's say, the last 10 or 20 years? And I think this is really nice summarized in this paper by Max Moe and Di Stefano. I'm showing you now, as a function of the primary mass of these binary stars, how they are, of these systems, how they are paired into single stars. This is the red line. And also how they are paired into binary stars, triple star system, even quadruple systems. And maybe to highlight and to guide your eye, I would just like you to pay attention a bit onto how single stars, or the fraction of single stars, evolves probably as a function of the mass of the objects. And for example, if you look into solar-like objects here on the left-hand side, you see that maybe, well, order of magnitude, half of stars are in higher order multiples, for example, binaries, and half of them are single. But if you go into the more massive star regimes, in particular into now maybe stars beyond 10 solar masses or so, then you hardly find any stars that are truly single. And this has quite some interesting consequences, as we've seen in this animation before. But you can also translate this observational picture essentially into answering a question of how many of these stars are going to encounter any of such mass transfer phase that we saw before. And again, this is as a function of the primary mass now of the objects. And you can see that this interaction fraction in binary, or in stars in general, really increases from, I don't know, maybe 20% or so from solar-like stars up to more than 100% in the most massive objects, in the O stars. And if you wonder now, how is it possible, more than 100%? Well, this really has just to do with how you normalize things. And remember, we have quadruple system, triple system in this whole kind of computation in here. But what this means is, if you then, for example, single out only the stars that are going to go supernova, here the situation is such that maybe 80%, 100% or whatever of all the stars, they have experienced a mass transfer in their past. And this is sort of the supernova that you're going to observe. Binary interaction or mass transfer, that can be quite diverse. And there you have several possibilities of what can happen. And I would like to highlight this a bit by looking into, let's say, the parameter space of binary stars. So what I am showing you here is a diagram for binary stars that all have the same primary star. And this is a 10 solar mass object. And you can pair this 10 solar mass object now with a companion that has a different mass, and the masses can then range essentially from something really low up to 10 solar masses. And this is essentially indicated here on the y-axis as this mass ratio Q. And then another important aspect, if you want to pair binary stars, is into what kind of orbit do you put them? Something that is really close and something that is extremely large. And this is sort of what is covered here by this initial orbital period of the binary stars. At the moment, maybe don't worry about the background coloring. You can just forget about that for the time being. But what I would like to tell you is, or maybe make you aware of, that you can view this initial orbital separation as an indicator of how evolved is your primary star when this phase of Roshlov overflow begins that we saw in this animation, this artistic animation previously. And depending now on where you are in this diagram, different really interesting things can happen. Maybe coming back to first of what we observed already in this animation, and this is sort of the reign or the region in this parameter space where stars would stably transfer mass from one component to the other. But then there are also situations where this mass transfer initially becomes unstable. And I think then things are really getting interesting, and there's a lot of stuff happening. For example, in this region here of the parameter space where you have this white hatched area, this is where we expect stars to completely merge with each other. And this happens then usually, let's say, in binary systems that have rather smaller initial orbital periods. And if this mass transfer becomes unstable in binary stars with initially larger, wider orbits, then the stars are going to evolve into what we call a common envelope phase. And common envelope really literally means what you probably expect is you have a companion star that is being dragged into the really huge fluffy envelope of a giant star, and then this companion spirals through this envelope. And there's in all of these dynamic encounters, there's a lot of physics going on, and I'll come back to some of that later in my talk. So the focus of this talk is going to be what all of this essentially means for the pre-supernova structures of stars and for the supernova explosions that you get. And in particular, I would like to pay most attention on to the compact remnants that are left behind by such binary stars that went through such evolutionary phases. Before I do that, I would like to show you two interesting applications. And I'm going to show you now a Hertzsprung-Russell diagram here. And this Hertzsprung-Russell diagram is populated by only binary stars. So the initial binary fraction is 100%. And the color on this diagram for the individual object is going to encode how fast the star rotates. One being it rotates critically, meaning that the equator is essentially flying apart. And I can just start this animation, and you nicely observe the turn-off, the cluster turn-off, main sequence turn-off in this in these stellar populations. But you also see all these little dots that appear around the cluster turn-off. And these are all the binary products that you produce via, for example, the merging, but also by this mass transfer. And these objects are, of course, well known to you. These are the blue stragglers. And there are many features already in this Hertzsprung-Russell diagram that would be worthwhile exploring further. But instead, what I'm going to do is I'd like to also show you if you take such stellar populations and you integrate them across the whole galaxy, our own Milky Way galaxy. And then you can ask questions like how many of the stars, in particular now I'm looking only into the O-type stars, how many of these O-type objects that we have in the galaxy already maybe did something with their binary companion. And this is work back from 2014. And I think there are a couple of takeaways from this. First of all, let's say roughly a quarter of stars in our own Milky Way galaxy, they are truly single stars and they will never sort of do anything with their companion. Okay. What I find really exciting is to realize that of the order of, let's say, 10% of stars, O-type stars in the galaxy, they are merger products, merger remnants. And other objects here are sort of the stars that have just accreted mass after such a mass transfer phase. And half of the O stars, for example, in this study, are predicted to be pre-mass transfer binaries. So this is maybe, yeah?
We have a question, so if we may interrupt here from
Yes,
Tony.
of course, please. Mm-hmm.
I just wanted a clarification. You mentioned blue stragglers in this context. I mean, there's also, people talk about blue stragglers usually as less massive stars, right? These aren't, they're just blue and they're straggling behind, but they're not blue stragglers in the normal way that's usually discussed, right? Just to make sure everything's clear.
Yeah, that's right. There might be some confusion about sort of the, I mean, this additional way of finding them is you look into, let's say, evolved star clusters, maybe at least 100 million years or so, and then they stand out very clearly. But what is also actually clear, that the same phenomenon can in principle be observed also in very young star clusters. So imagine you had a star cluster of 10 million years only. And already in such a star cluster, you would have, I think, what would qualify under the term of a blue straggler. But sometimes what I tend to do is I would say it is sort of the massive counterpart of this classical blue straggler.
Yeah, okay, that's helpful. And
yeah,
then, and either like the SANA results, or even if I incorporate Ova when she's, you know, looking at the Magellanic clouds, do people see these massive blue stragglers pretty clearly in observations? Yeah, so they're a bit difficult to pick out in observations. Maybe I can actually restart the this animation, and then you can, well, I can't stop it now, but this is only a cluster of a few million years. And you see how extremely populated this turnoff is. And observationally figuring out which star is now
a true blue straggler and which is just what is the turnoff. That is the difficult part. But I think from the standard binary evolution aspects, these guys are going to be around pretty much as soon as the very first star leaves the main sequence, because then you had enough time for close binaries to already start these mass transfer phases.
Great, thank you.
You're welcome. Okay, so this was more about, let's say, the galactic environment. But what I also find extremely exciting is to think about cosmic reionization. And massive stars, as you know, they are pretty hot and they have luminosities of up to 1 million or so of that of our own sun. And so this enormous luminosity can, of course, ionize a lot of hydrogen in principle. And even more so, we're talking here about binary stars. You can take off the envelope of such a star, and what is left is something that has an even higher effective temperature. And so that gives you even more maybe ionizing radiation or harder ionizing radiation. And as you all know, Ilva has done some fantastic work on this. And here, for example, I'm showing a plot from her paper showing you what is the emission rate of hydrogen ionizing photons across cosmic evolution. This is, of course, more like a toy model, but I think it still gives you a good impression of what is probably happening also in our cosmos. And you can see it at high redshift, for example, the massive stars are totally dominating this ionizing budget of photons. And the stripped stars here that I just briefly mentioned, they're already contributing quite a bit. And if you integrate this all up for the end of the phase of hydrogen reionization, roughly here at a redshift of 6.5, then the massive stars have contributed the biggest chunk, but these stripped objects might have contributed sort of, let's say, of the order of 20% to the whole ionization. And there are other studies that find something similar. So I'm showing you now results from the Sphinx cosmological formation simulation. And they have two suites, one where they only look into have single stars in there, and then another one where they also included binary stars. So the single star simulation is sort of in red here, and the blue curve is for the binary model. And what you can observe, for example, here is that the ionization fraction, or this is the neutral volume fraction of hydrogen, is extremely low already in this binary population, maybe at a redshift of 7, whereas it only reaches such low values in the other simulation, maybe at a redshift of 6 or maybe even later. And to also get a visual impression of this, I think these people here in this paper, they produced absolutely some striking images. And this is looking at the redshift of 6 into both of these simulations. And just visually, you can immediately figure out that if you have these binary stars around, there's much higher rate of hydrogen photoionization happening in this simulation. So this is it for, let's say, the binary stars in the cosmic sense. But I would really like now to dive into what does this mean for the supernovae that we get from such stars. And I would like to start with these stripped objects, because we just talked about them and they're extremely exciting. And the way I would like to start out here is to show you the graveyard of stars. And this is I think already a pretty famous diagram that is being produced by the LIGO Virgo consortium. And soon, I believe, I won't be able to show this anymore on any slides because of finding so many more sources. But this is a compilation of different compact remnants. Sort of on this axis here, you see the stellar mass of these stars, of these objects. So down here, you have neutron stars. And these are neutron stars that have been found primarily in our own Milky Way galaxy. And you find them, for example, in double neutron star systems or neutron star plus white dwarf binaries and so on. And then you have electromagnetic black holes, as they are called here. So these are black holes that people have found in X-ray binaries, also again in our own galaxy. And then in blue, these are all the sources from gravitational wave observatories as far as the O3 run for LIGO went on. And there are a couple of features in here that I would like to highlight. So first of all, you may have noticed that there is a dearth or so of compact objects in this mass range from 2 to 5 solar masses. I'm saying this is maybe not exactly a gap because there are a couple of objects in here, and I put a couple of more references also here on the side. And there's a lot of interesting developments just happening from the observational side of how many objects do we really have in this range. But it seems as if there was at least a dearth of objects in this range. And then another striking feature that people realized soon they had got these results is that in our own galaxy, we essentially find no black hole with a mass of 20 and plus and onwards. But from the gravitational wave emission, we actually see many. And this might sound to some people as a contradictory or some missing physics or whatever. But I'm going to show you in a moment how you can easily interpret this, and I think it's going to make sense. There's another aspect that is extremely interesting, but that's something I'm not going to touch upon. And this is the spare instability supernova mass gap. So there are some extremely massive stars that might undergo this pair instability. And whenever they undergo such a pair instability, the whole star might be just blown apart. And then there is literally no remnant. And the predictions from theory are pretty clear that there should be at some point a mass gap. But of course, you can easily populate this mass gap in many, many different ways. But that's another story. The bottom line that I would like to draw from this graveyard is the following. If you look into all of these objects, then I think it is fair to say that essentially all of the systems for which we have gained mass measurements of the neutron stars and black holes, or almost all, I would say, have experienced a binary mass exchange history. So there was some mass transfer in the past, and meaning if you want to fully understand why stars have, or these compact elements have the mass they have, then this is something that we have to look into. And I brought a little sort of a cartoon on what I really mean by that. So this is one of these what are called sometimes Vandenheuvel cartoons, because I think Ed was one of the first persons really to introduce them. So imagine you start out here on the left with two zero-age main sequence stars in a binary. And then there is our phase of mass transfer that I discussed earlier. You remove the hydrogen envelope, you're left with a helium star. The helium star eventually explodes in a supernova. And then you have a neutron star paired with another still sort of living main sequence star, for example. This could then give rise maybe to a high mass X-ray binary phase or something similar. And in this simulation, then again, the star that here has accreted mass previously, again, increases its size and might end up evolving through a common envelope phase. And only thereafter, you have then in a very tight binary, this neutron star plus a helium star. There can be maybe some further mass transfer happening, and ultimately the helium star also explodes. And what you're left with are two neutron stars in a tight binary that can then merge in Hubble time. What I really want to highlight is that these evolutionary paths, and I'm only highlighting here now an evolutionary path within what is known in the community as sort of this isolated binary evolution. So I'm completely putting aside at the moment dynamical environments like dense star clusters or nuclear star clusters or disks in AGNs and stuff like that. So this is really just for isolated binaries. But in any case, these neutron stars, these compact objects, in particular the firstborn compact object, that is the first sort of mass transfer phase here, this neutron star evolved from a star that has lost its envelope. It is clear that the supernova light curve is going to be affected. It's no longer going to be a type 2 supernova, but something like 1bc. But the question is what happens to the core evolution? And this is something that we recently looked into. And for that, I have to maybe tell you a bit more about these mass transfer phases. Essentially, there can be different phases in the evolution when you remove the hydrogen envelope of a star. So I'm showing you for that purpose here a diagram of the radial evolution of a star as a function of age here. And then I'm indicating a couple of points where you could maybe think about stripping off the envelope of the star. And also maybe to get this a bit more visual, what we call then case A mass transfer is when you still have a core where hydrogen is being converted into helium. And then at this point in the evolution, you remove the hydrogen envelope. I think it is immediately clear that the situation might be different if you have what we call case B mass transfer. That is, once the star has finished core hydrogen burning, so we have established a helium core, and then there is a hydrogen shell burning source surrounding it. And if you were to remove the hydrogen envelope in this phase, then maybe the evolution is going to be different. And there's also usually a case C, and that is if mass transfer only starts after the star has also finished core helium burning. And in that case, you would have a carbon-oxygen core. There can be then a helium shell burning source, a hydrogen shell burning source, and then this is only the outer hydrogen envelope that you're going to remove. And depending on really now on when you remove this envelope, the evolution can be modified. And what people have realized already in the past is the following. If you want to understand how the star is going to end its life, and whether you get in a supernova explosion or not, and how this whole advanced burning cycles in massive stars proceed, then what you need to know really is, how does this core of the star look like after core helium burning finished? So at this point, what people usually consider the evolution to be is that it is biparametric. And biparametric, why is that? Or what are the two parameters? The first one is essentially the core mass of the star at this point, which I'm just denoting here as the carbon-oxygen core mass at the point when core helium burning has finished. And the second parameter is, how much carbon do you still have in the core? And for single stars, they follow this nice curve. So there's a one-to-one relationship, and the initial masses of these objects are indicated here on top. And for example, what I'm highlighting here also is sort of this gray shaded areas, and they are really relevant because in this gray part over here, these are single stars where the onsetting core carbon burning phase proceeds under radiative conditions, and it proceeds under convective conditions here on the left. And then the other gray shade is for neon burning, but I'm not going to really go into this. But these are the two parameters that are thought to tell you how the star is going to end its life. And in single stars, this is how it looks like. For the case C systems, when you only remove the envelope after core helium burning has finished, well, you get exactly the same by definition here. But then the case A and case B stripped stars, they form a separate sequence in this diagram. And so already from that, you can conclude that the cores of stripped stars are also going to evolve differently than those of single stars. So this is an important realization that one has to keep in mind here. And this has, of course, and this is what we then looked into, has consequences also for the structures of stars at core collapse. One quantity that people often consider is the so-called compactness. And I'm just defining this compactness parameter up here. It's essentially a measure of the mass-radius relationship of stars. And it is measured often at a mass coordinate of 2.5 solar masses. So again, this is the same CO core mass function as before, but now you see the compactness parameter. And I think more importantly, what you observe is this is a gray shaded area where this behavior of carbon burning in the center from burning under convective conditions, moving over into radiative conditions changed. And you can see that whenever this change occurs, there is a jump in compactness, and you produce what we call a compactness peak. And then the compactness actually drops again once more, and then finally it reaches high values. Traditionally, people had tried to predict what kind of compactness values would lead to black hole formation, which for neutron star formation, and maybe as a rule of thumb, at a compactness parameter here of 0.45. This is maybe a threshold, and so you can maybe guesstimate from this already that these objects here in the compactness peak are maybe going to produce a black hole, and the stuff or the stars down here may be going to produce neutron stars, and then you have black holes again from this part. And what I wanted to show you now rather is how these stripped stars look like in this diagram. So the KC systems are again relatively similar. There's a bit of noise on here, which is due to numerics in our simulations. But then the case A and B systems, they are generally different. They show you a different landscape of compactness parameters. For starters, this compactness peak has been shifted, and there is also a much larger range here of CO core masses that allow probably for neutron star formation, because the compactness is relatively low in these objects. And then only later on, the compactness again goes up to large values. And so the second message from this is that also at core collapse, these stripped stars have a different pre-supernova structure. And then we went on and asked, what does it mean for the supernova now? And we've been looking or using then a semi-analytic supernova approach here. This is just a sort of a model that looks into neutrino-driven supernova explosions and then explores what is the outcome. So this is a quick code or a fast code that you can easily apply, but it might not be, of course, or it is not as accurate maybe as some other big simulations that you could be using. I would like to highlight a few things now. And the first is for the compact remnant masses, of course, neutron stars and black holes. I think the most instructive panel or plot here is the left one, and the right one is maybe for the experts in the room. Here I'm showing you as a function of initial mass, what is the final remnant in terms of its neutron star mass, down here, and the black holes up there. In blue, this is again the single star sequence, and as expected, you have this compactness peak from this change in core carbon burning conditions. And then we produce black holes for all the other objects up here. One important thing that I would like to mention is in the single stars, we have a transition from neutron star to black hole formation in these models at the moment at an initial mass of 35 solar masses. This is also roughly the same for the case C stripped objects. If you now, however, look into case A and B stripped stars, you can see that in these objects, we can produce neutron stars maybe in the simulations up to initial masses of about 75 solar masses. So this is a huge difference. And also in more general terms, I can say that our stripped objects, the stripped stars here, are always on average easier to explode compared to their single stars. And maybe for the experts in the room, of course, plotting things as a function of initial mass is a bit unfair, and you should really consider the same core masses that stars develop. But then the picture is again the same. For high core masses here, stripped stars can explode and produce neutron stars, whereas the single star equivalents, they would probably rather collapse to a black hole. I'm just highlighting these things here once more, and I would also like to draw your attention to a couple of situations where we find that supernova fallback might be expected. Okay, I would also, yeah.
We have another question from Tony. So before you move to next slide, probably he wants to ask something here.
Yeah, I mean, maybe you're going to come to this, but where are all the 4, 5, and 6 solar mass black holes on this that we see in our galaxy?
Yes, that is a good question. Let me just go to the next slide, and I think you'll see where there might be.
Okay, good, thanks.
So we have then just sort of taken our results and put them all together into just a histogram, integrating over some initial mass function. And this is sort of the picture that you get left for the neutron stars, and this is for the black holes. And as I already mentioned, or as I maybe highlighting already too, this is sort of our default settings here. And I would like to mention a couple of things. First of all, the stripped stars produce neutron stars that are on average less massive by about 0.05 solar masses. So it's maybe not too much, but it's still something that we find in these models. We have for sure some neutron stars that are born massive with masses maybe up to, in principle, 2 solar masses, but the sampling here is maybe not high enough that we can see these objects also in our sample of stars. And then there's this mass gap that you already spotted. This mass gap is here in this default set in the range of 2 to 9 solar masses. So there is no 5, 6 solar mass object in this default set of computations. You can again see the black holes here. The lowest mass black holes that we have are from these objects in the compactness peak. And what you can observe, which is also already really interesting, is the maximum black hole mass that we find in our stripped stars here is of the order of 20 solar masses. Yeah, and the reason here is simply these stripped stars, well, they have lost the hydrogen envelope. So the remaining object is a helium star that has a strong stellar wind, and then under galactic conditions, this means that we could not find really anything that is much more massive than 20 solar masses, which might immediately help you to lift this tension that I mentioned earlier in the stellar graveyard. Okay, but now really coming to your question about this mass gap, because this is something really interesting here. I told you that we have encountered a couple of stars where we expect supernova fallback. So meaning the supernova might not be energetic enough really to eject the whole envelope and the whole material. And we have a couple of indications of such objects. And what we then assumed is, well, given that we really don't know from our modeling how much of the ejector mass is going to fall back, let's just assume that 50% of the ejector mass actually falls back and then adds to the compact remnant mass. And if you make such an assumption, you are going to partially fill this mass gap here. And here in this case, if you assume 50% fallback fraction within our modeling, we would narrow down this mass gap to 2 to 5 solar masses. I do not want to claim anything like 50% fallback is needed, blah, blah, blah. That would all be completely nonsense. But I think the more general concept here is one that should stick. Namely, that probably the fallback is going to really determine and define how big this mass gap or how big this mass staff is going to be in the end. So it's supernova physics, I think, that sets this range of mass gap or mass half. So this
And
is the message.
And just to be clear, this fallback is hydrogen-rich material?
Not necessarily only, no. This can also be, let's say, oxygen-rich and carbon-rich material. So it's
Okay.
also the parts. Yeah, so maybe in the beginning you form a proto-Neutron star, maybe of at most 2 solar masses or so, but then the carbon core, for example, of these objects is much, much larger. So this is also partly the fallback that could maybe go back into the stars and form a black hole. All right. I would like to just highlight 2 more things just briefly before I would like to show you a bit also what happens to stellar mergers. First of all, we figured out that the explosion energies of our stripped stars are on average higher, and they are on average higher by 0.2 beta, which is, I think, quite a bit. And similarly, we figured out that the produced or synthesized nickel mass in these stripped stars progenitors is also going to be larger compared to the single stars that we have. And the difference here on average is of the order of 0.02 solar masses. So it doesn't sound maybe too dramatic. It is interesting to note, I think, that there is quite some evidence nowadays from the observational side that sort of type 1b/c supernovae produce more nickel than maybe type 2p's. But I think the observational biases and other things are really difficult to overcome. So maybe someone here in the audience has some better understanding of that, and I would be very much interested in that. Within our models, this also means, in fact, that the kick velocities of stripped stars are going to be larger. Yes, so I think there's a question.
I'm sorry to interrupt again. We have another question. People are really excited about this topic from Kyle.
That's great.
So yes. Please, Kyle.
Yeah, just a really basic on the previous slide and this one too. What's the metallicity that you're assuming?
Oh, I should have mentioned. Yeah, these are all solar metallicity stars.
Solar, okay. Solar.
I'm sorry, should have mentioned that. Yeah, thanks for the question.
Perfect.
Yes, so there are systematic differences that come from envelope removal that have that then propagate to the core collapse phase and probably also into these properties, which I think is quite interesting. I would now like to use maybe the next 5 to 10 minutes or so to also talk about stellar mergers, because this is something close to my heart, and we have done a lot of work on this. I would like to start out maybe with something that probably many people here in the room know. So this is a Hatchimal diagram. And this is just to illustrate what happens if you have 2 stars, 25 and 19 solar masses. They are going to merge, and then they form a merger remnant of 42 solar mass in this model. And the interesting thing is, for example, here this merger remnant undergoes supernova in a range where it is probably classified as a yellow hypergiant or so, and not as a red supergiant. And this is, of course, something that people have realized also in other instances. And I believe if you think about supernova 1987A, the progenitor here was a blue supergiant, effective temperature of the order of 16,000 Kelvin. And it also produced this unusual bipolar ring nebula, where you have an artist impression down here, and this is a real picture of this. And there are, of course, models that are interpreting this whole nebula structure and the reason why the star exploded as a blue supergiant and not as a red supergiant via such a merger channel. This is extremely interesting. There's a rich body of literature down there that you can maybe consult. And I also would like to highlight maybe one other aspect here that we've been recently working on. And we've also been trying to interpret the great eruption of Eta Carina within a merger scenario. Again, you have sort of this beautiful bipolar-like structure, and this is an extremely energetic event. But this is not what I want to talk to you about today. This is maybe for another day. But instead, I would like to turn the attention now to magnetic fields. And we had a question a couple of years back, and that is, we wanted to know that if 2 stars merge, whether this merging can also amplify magnetic fields. And we had a specific star in mind. This is this magnetic star, massive star Tau Scorpii. And we wanted to match and wanted to produce an object that looks like it. Tau Sco, in this case, is a blue straggler, by the way. It lives in a roughly 11 million year old OB association. And it is strongly magnetic. It has a strong magnetic field at the surface. And in general, in the massive star or in the OB and A type stars, roughly 10% or so of these objects are found to be magnetic. So they have large scale, strong magnetic fields. And the question really is, why why do 10% of stars roughly have that and the others don't? And we wanted to know whether merging can do this. So we turned to the beautiful moving mesh code AREPO that has been developed by Volker Springel, and a lot of these MHD capabilities have been implemented by Rüdiger Packmore. The code was originally really used for large-scale cosmological structure formation simulations. And I'm showing you a German stamp here that was made for the Illustris simulation. And it is really a masterpiece, this code. And then a PhD student here in Heidelberg, Sebastian Ullmann, at the time, adapted this code also to stellar astrophysical applications. And a lot of the things that I'm going to show you now are really based on his successes with that. So I want to show you now what happens if a 9 and an 8 solar mass main sequence star, if they are going to merge. Again, this is galactic metallicity. And I'm just showing the video, but of course, it might not come across so nicely. So I have some still images in a moment. On the left-hand side, you observe density in the equatorial plane. On the right-hand side is the magnetic field. So you might remember from the beginning of the simulation, there was literally no magnetic field in the beginning of the simulation. There was some really micro-Gauss strong seed field, and this seed field has been amplified in this whole process. And we were able also to pinpoint what is this amplification agent here. And it is the well-known magnetorotational instability that initially amplified the magnetic field. This may be known to people that work a lot of on accretion disks and stuff. And this is something that kicked in this simulation. So here are maybe the still images, so I can explain maybe roughly what has happened here. In the top panel, I'm again showing you the absolute magnetic field strength in the equatorial plane, and the density here in the equatorial plane, and the lower panel is in the edge-on view, sort of the XZ component. So what we have is two stars in a close binary. They are even in an overcontact configuration, and there is mass transfer from the more massive star onto the companion. And it is then in this mass accretion stream that shears on the surface of essentially then both stars later on in the evolution, that the MRI is active and then starts to amplify the magnetic field. But then also later on, once here, for example, the two cores of the stars are finally going to merge. So in fact, the core of the primary star is entirely disrupted here. And then in this final merger phase, so I'm trying to highlight this in this little inset down here, this is also where we do see Kelvin-Helmholtz-like instabilities that are probably helping further with this magnetic amplification process. So ultimately, we have really then produced a merger remnant that is highly magnetic, and it also has quite a peculiar structure. And for that, I would like to draw your attention to the bottom right panel here. And this is the density edge-on view after 5 days of this core merger. And we have now a roughly spherically symmetric remnant in the center, which has a total 14 solar masses. But there's also this massive and huge torus just surrounding the object. And this is the torus that is now storing most of or a lot of angular momentum. And the torus in total has a mass roughly of 3 solar masses. So this is how this merger remnant really looks like. And then we put a lot of emphasis and work into getting such a merger remnant back into a one-dimensional stellar evolution code, such that we can also then fast forward the evolution up to core collapse, essentially. And maybe I'm going to skip this slide with the technical stuff, and maybe we can discuss this at a later point. But rather, I would like to show you maybe how the star evolves in the Hertzsprung-Russell diagram and what kind of supernova we might get from such a star. In total, the merger remnant has a mass of roughly 16.9, or let's say 17 solar masses. And I'm just showing you how a single star of that mass would evolve in the Hertzsprung-Russell diagram. So here's its main sequence evolution, the nice Hennier hook when it is running out of hydrogen fuel in the center. And then it rushes over to the red giant branch, and then finally climbs the giant branch to explode here as a red supergiant. The merger remnant that we have produced has a somewhat different evolutionary phase. We start out here, and the color now on this curve indicates the spin of the star. 1 in this color code means that the star rotates critically, so it's almost flying apart, and then 0 would be it doesn't rotate at all. So we set up this star, of course, to be fast rotator. That's how it looked like right after the merger. And then it starts out here with a puffed up envelope, just all the energy that has been dumped into the star. And the star has to thermally relax. It has to radiate away essentially this excess energy that has been dumped into its interior from the merger. And in this relaxation phase, it is first of all going to increase in radius and also brighten up. And funny enough, during this evolutionary phase, the star spins up. Yeah, so this is maybe completely counterintuitive to what you might be expecting from standard angular momentum conservation. But I would like to highlight here, maybe just in saying that the the momentum of inertia of this star is pretty much unusual. And this can actually lead to such an evolution. And then also later here, you see the star contracts back to the main sequence. And in this contraction phase, it actually spins down. So in this model, where we have actually had to put a lot of assumptions into, and feel free to ask me and question me on all the assumptions later on, we then figured out that it is possible maybe that from such a merger event, later on, once the star is back on its main sequence evolution, the star is maybe rather a slow rotator. And in this particular instance here, we were lucky enough to also match the observed position of tau SCO in the Hertzsprung-Russell diagram. We were also able to somewhat match the rotational velocity of tau SCO, although I have to say tau SCO rotates even slower than our merger remnant over here. And then we could also follow the further evolution of this merger remnant up to core collapse. And because we merged two relatively unevolved stars, the object rejuvenated, and we essentially got a star that evolves very closely to the single star, but just at a somewhat higher luminosity. And this is just has to do with that the star now has a higher helium content too. But ultimately, we do get then a type 2 supernova from such an object. But of course, this is a star that is maybe highly magnetized in its interior. And this is, I think, an interesting prospect. Well, I should say, and this is just a reminder to myself, there are a lot of open questions in this whole evolution. I can probably give you a whole seminar on that separately. Just keep it at the moment with some caution here. But I would like to hypothesize maybe on the final fate of such an object, because I think this is really interesting and has some interesting, maybe interesting consequences too. So I'm showing you in the background our Van Gogh-like illustrations of how this merger remnant might look like. So this is the equatorial plane. The color is essentially the absolute magnetic field strength. But then I hope even across zoom you can see that there are some streamlines sort of in this image, and they are supposed to indicate roughly the magnetic field orientation and the direction of the B field. And this little inset over here is showing you sort of the view onto the central merger remnant from the edge on. But anyhow, so we of course had to ask ourselves the question: so what happens to this magnetic field, and what does it maybe mean for this for the neutron star that is being formed? And what we only could do at the moment is that we can assume maybe that this magnetic flux that we have produced right after the merger, that this is maybe conserved up to core collapse, or maybe at least some fraction of it is conserved to core collapse. And so what we did is we said, okay, let's take the magnetic flux in the innermost 1.5 solar mass region, so somewhere down here where my cursor is currently pointing it. And if this magnetic flux is conserved, and in particular you have to recall that this core of the star here is relatively fluffy compared to, of course, the density of a neutron star. Just to indicate this, if you were to take a teaspoonful of material from the center here, you would get maybe something like 10 grams. But then in this final merger, final collapse phase of the star, when you form the neutron star, then a teaspoonful of material would maybe have a mass of 10 to the 9 tons. Yeah, so this magnetic flux, if this would be conserved from here, would allow you maybe to reach surface magnetic field strength for the neutron star of up to 10 to the 16 Gauss. And maybe the people in the room that know magnetars, which are literally the strongest magnets that we know of in the universe at the moment, they have been observed to have surface magnetic fields of up to 10 to the 15 Gauss. So we are in the right ballpark, which was really quite surprising to us, to be honest, and that has excited us a lot. I should also say that from our default model here, just to remind you, we expect this neutron star remnant to be rather slowly rotating at this point. But again, I maybe should have put a couple of question marks behind this slowly rotating part here. Anyhow, I think this is an interesting prospect, and so we thought a bit more about this, and we were asking ourselves: so does also this magnetar formation rate match with what we know from the incidence rate of magnetic massive stars? And a back of the envelope computation could be like the following. People try to study how many magnetars are formed in our own galaxy, and here's one guesstimate of this number. this order of 0.3 magnetars that are formed per century in our own galaxy. The galactic supernova rate, as measured from the radioactive decay of aluminum in our own galaxy, is of the order of 2 per century, and that would give you a magnetar birth fraction of roughly 15%. Or let's just put it back to orders of magnitude. This is again sort of order of magnitude 10%. And this is the same, just to say again, as that of what we observe for strong magnetic fields in massive stars. Roughly 10% of them have that. So this is something that really excited us. But I want to also highlight, maybe before people get too excited here, these objects that we are expecting here, they will not be sort of these magnetars that people discuss in magnetar-driven superluminous supernovae or so, because then you really need extremely fast rotation. And probably we're not going to have this in such merger remnants. But what this channel might be actually relevant for is to form maybe highly magnetized neutron stars. And this could, of course, play a role maybe for soft gamma repeaters that are known to occur in such magnetars. And also nowadays, or since probably the summer of this year, we also know for sure that some fast radio bursts are connected to magnetars. So this is sort of what I wanted to show you and tell you maybe a bit of like a hypothesis on what might be the final fate of a main sequence merger later on in terms of its neutron star. So this brings me to the end of my talk. And maybe I can briefly summarize the main aspects. I think one take-home message for you is, and probably you anyhow know this already, that we expect the vast majority of supernovae from stars that had some sort of binary mass exchange in the past, and this mass exchange can be quite diverse, as I've shown you. Also, I think what is always interesting to realize is if you look into the neutron stars and black hole masses in X-ray binaries, in neutron star binaries, from gravitational wave mergers and so on, there's an extremely high chance that at least one of these two compact objects went through a phase where the star has been stripped of its hydrogen envelope. And at this point, we have to take this into account because we now really know how this envelope stripping affects the core evolution of the star. And just to repeat, these strip stars are probably easier to explode. They produce neutron stars over a much larger initial mass range. The neutron star and black hole masses are on average smaller, and so is the explosion energy and the kicks and the nickel, but here you actually produce more in the strip stars. On the stellar merger channel, merging of main sequence stars could maybe produce strong magnetic fields, and if these magnetic fields might persist up to maybe the supernova stage, then maybe this is actually a channel to form highly magnetic neutron stars, sort of these magnetars from already highly magnetized stars. What I didn't talk to you really about is what these findings for the strip stars really mean maybe for the predictions of black hole merger rates and so on. But maybe just as a peak preview here, we expect that compared to some of the engines that you find in some of the predictions, in particular this Chris Fryer's 2012 predictions, we would expect much fewer black hole mergers from such objects, simply because the strip stars in our models are no longer going to produce black holes, but often enough they're going to produce a neutron star. And so this should then reduce the predictions from black hole mergers. But we're currently working a bit more on this to figure out how much this really does. And I think with that, I would then like to stop here. So I hope that I'm somewhat in time, given that we had a couple of questions in between, but I would be happy, of course, to discuss more with you guys now. So thank you very much for your attention.
Thank you very much, Fabian, for this very exciting talk. I think you show, of course, really interesting research. Knew a little bit of before. So I would like to ask if anybody has any questions before I go ahead and ask all of my questions. You can raise your hand on the side. I think it got changed and it's inside of reactions now.
I mean, I guess I'll just ask one question real quick. So you were showing it was interesting that the carbon abundances were different for the binary, the stars that had binary interactions, depending on when they had the binary interactions during their evolution. And I was just curious, has this been compared with the supernova remnant of Cas A, which there's been some controversy? It looks like it was a type 2b, and there's been some controversy whether it was a binary progenitor or a single star progenitor. Maybe this could help with that.
Yeah, that's a good question. So what we have not yet worked completely out is how much of these chemical differences that we observe at this point now at the end of core helium burning would persist also at the core collapse stage. I can tell you, of course, that this, in particular, this carbon abundance is going to be different, in particular in some outer layers of the star that are not going to collapse into a neutron star or black hole. So you have some, so the expectation here is that the strip stars produce a bit more of carbon. My expectation, without actually having done any of the computations yet, is that the oxygen abundance probably stays roughly the same. So you can't expect much here. But then later on, also in the synthesis of chemical elements, once you have this shock wave that goes through the inner parts of the of your star and then converts some of the elements, I expect that there are some differences in these stripped objects, simply because the well, first of all, the chemical structure is already a bit different, but then also the explosion energies, for example, are somewhat larger, and so you can also expect higher post-shock temperatures and maybe then different chemical yields in the end. So we have not worked out the details. And also, to directly answer your question, I'm not aware of work that tried to do this with Cas A, but that might simply be that I have not looked for this. So I can imagine that some people have actually worked on this, and yeah, so maybe we would have to check the literature, really.
Yeah, something to keep in the back of your mind. But
yeah,
thank you.
Yeah, sounds good. Thank you.
Okay, Kyle, go ahead and ask your question.
Yeah, thanks for the nice talk, Fabian. It was really nice. So there's a lot of evidence that the majority of stars are formed in clustered environments. So most of these clusters would dissolve, on the time scale of tens of millions of years or so. But that should certainly give plenty of time for the dynamical processes to influence the massive star evolution. Can you maybe just say a couple comments on if you thought a bit about this at all? Yeah.
Yeah, that is, of course, completely true. And I like to just make my life easier by restricting myself to this isolated binary evolution, because then we can kick out some of the uncertainties. I think it is instructive to look into this parameter space of binaries to answer your questions a bit. Because, a cluster environment is not a cluster environment, but it really depends on what is the density in your cluster. And in particular, what I would like maybe to point out here is the following. The stars, for example, that are going to merge, they come from really initially tight binaries. And they are probably so tight that maybe the average interaction in a dynamical environment has hardly the chance to, for example, harden the orbit or so, simply because the orbital energy is going to be really so large that you have to have an extremely energetic encounter in a cluster environment. Then, of course, if you go to initially wider binaries, then, of course, maybe the dynamics can really influence the binary orbit. And this would then maybe affect objects that could or would be expected to go through common envelope evolution. So that affects some of the strip stars that we discussed here. And also, in principle, in the common envelope phase, you can have mergers too. And maybe it also affects some of those objects that we expect to have stable mass transfer. My naive expectation is probably that these cluster, maybe I should actually add these little things so that you get an impression of what the individual things are. My naive expectation would maybe be that whenever you have these encounters, you can probably induce maybe even further binary evolution. Maybe you can make orbits a bit eccentric, or maybe you can push stars together. Maybe you can trigger some other instabilities in orbits and so on. But probably you can tell me actually more about this, how much this really does. The interesting point always is simply to figure out, is it a hard binary that you're trying to influence here, or is it a binary that the dynamical encounter can really do something to?
Yeah, thanks.
Okay, so we have time for some question. Alex, I can see your hand.
Yeah, thanks. So that was really awesome. I have a question about, so you mentioned that once the star is stripped, then it continues to lose a lot of mass from stellar winds. And I'm wondering, as you sort of dial down the metallicity, I guess you haven't done a full investigation of this, but do you expect the differences between the stripped stars and the single stars to continue to exist, or is the lack of the stellar wind or the lack of a strong stellar wind at that stage going to sort of remove that?
Yes, so in principle, you can think about two directions to go. You mentioned now the lower metallicity direction. So what this stripped star in a binary always does is it removes the hydrogen envelope. And then you're completely right. If you then further go down in metallicity, that means then that this helium star that you produced experiences less strong stellar winds. But this is also true for the standard single star. So this difference, in particular in low metallicity environment between stripped and non-stripped stars, is always going to be that you have already removed the hydrogen envelope. But it is then going to be harder, I guess, in such low metallicity environment to, for example, also remove much of the helium via then a stellar wind. Yeah, so this might affect later on the 1b, 1c supernova branching. Now let's take the opposite direction. Let's ask what happens if you go to higher metallicity. That's something that usually people maybe don't do so easily, but this is also interesting. Because if you were to go up to higher metallicities, again, there is going to be this difference of the hydrogen envelope that you can remove in a binary. But maybe even if the metallicity is high enough, much of this hydrogen envelope is removed anyhow by a stellar wind. This is, I think, really interesting, an interesting question. I don't have a direct answer to this, but the naive expectation is, of course, that if you go to a higher metallicity, the winds maybe by themselves can remove already a large part of the envelopes. And I've played with this in a population synthesis code, but I don't have my plots now with me that I could show this to you. But this can similarly, in fact, then affect also the production of neutron stars, for example. So you can view the higher wind from higher metallicity, for example, as something that acts a bit like envelope removal in a binary. And so then you can produce probably neutron stars from a much, much larger range of initial masses. I think that is interesting. And maybe while we are at this topic, I think I forgot to mention actually one important aspect once we looked into this distribution of the remnants. And that is, in these models, I have not accounted for any luminous blue variable phase. And this luminous blue variable phase is maybe really only active in pretty massive stars, sort of in this maybe objects that cross the Humphreys-Davidson limit or so, or that at least get close to this limit. And we have indicated the stars here in this diagram where we expect maybe that the object or the star would evolve through such a phase. And we've only indicated this for the single stars. And maybe some people noticed that in these models that we've done, maybe even in the galaxy, we could produce a black hole of masses, 35 solar masses or so from our single stars. But this only is true if there was no LBV phase, which of course there is going to be. So these masses here of these black holes from the single stars, they're going to be lower because we have not included this channel here.
Okay, and so to give you a little bit of time before your first meetings, Fabian, I just want to ask my question super quick, and so you have to answer really quick. Okay. Do you think that mergers don't give rise to the VE type phenomenon?
Short answer, I think they do, yes.
But it's just a low mass counterpart.
It is in particularly a counterpart that leaves some accretion or disk material. I think that gives you then this emission feature in the spectrum.
Oh, cool. Okay, but rotation, is that still there or not?
I think so, yes.
Yeah, okay.
It is going to be there, yes.
Okay, so let's thank Fabian again for this very nice talk and the virtual visit, and I will stop the recording.